Hello, we're a Janusx team from Carlos III de Madrid University, and these are proposals for the Nanostar project. The team composition and labor assignment can be here consulted, as well as our associated supervisor. Due to the time constraints imposed on the present video, we will focus on a solution rather than on recalling Nanostar project requirements or statement. First of all, my colleague Pedro is going to introduce the diverse payload the mission will consist of. As we already know, payloads are the main and sometimes only driver of a space mission.
Although not stated in the mission requirements, we decided to elaborate a little bit more about the payload, because this is what ultimately justifies a mission. Our primary payload is this small low-power camera. Its specifications are pretty similar to the ones described in the Nanostar mission requirements document. For the secondary payload, we did a trade-off analysis between an off-the-cell spectrometer that we estimate will have a limited scientific return, and the development of a new broadband infrared spectrometer that would allow us to study the 3-micron peak in the water spectrum. The problem with this approach is that the cost associated may not be justified for a flyby mission. The current configuration includes the off-the-cell spectrometer. However, we would like to propose an alternative experiment. It turns out that in 2024 there will be a solar maximum, and we will be flying by a really interesting region for space environment studies. We would like to equip our spacecraft with instrumentations for the study of solar wind-moon interaction and also Earth's magnetotail. This has already been done by NASA's Artemis mission back in 2010, but we expect that now this technology would allow us to miniaturize a lot of the instruments. The changes to the spacecraft architecture are expected to be small if selected instead of the spectrometer. We could generate very useful data, for instance, for the radiation shielding of the Deep Space Gateway station. Also, the scientific return would be high.
Once the payload's operation has been specified, it is time to develop each of the different mission aspects. Among the most relevant, one can find the mission geometry, which is strongly affected by the parking orbit the launcher leaves the spacecraft in. One of the most successful launches in history is the Russian Soyuz. Indeed, Arianespace has recently acquired the grant to operate it in Kourou spaceport. Our initial orbit is thus a geosynchronous transfer orbit that combines the parameters herein specified together with the inclination of the Moon's orbit at departure epoch. This is due to the arbitrariness left for the team in selecting such an orbital parameter. Due to the mission nature, it was the opinion of the team that a patch-conics approach may not give the required insight on the underlying orbital dynamics, especially if electric propulsion is selected. Thereafter, a planar-bicircular four-body problem MATLAB model developed by Nereida where a dimension master thesis was employed as suggested by Manuel Sanjurjo Ribo. In addition, drag and solar radiation pressure were also included in the model in order to assess their implications in the transfer. Nevertheless, Earth harmonics have not been included mainly due to the model architecture, which is two-dimensional. It was thus the opinion of the team that the implementation was not worth the effort for a preliminary analysis, especially recording data derived from a potential field. The very first and obvious approach was to determine a single impulsive maneuver performed on the parking orbit perigee. For this purpose, the 4U green monopropellant fuel Aerojet MPS-135 was used. It features a maximum thrust of 1 Newton and a specific impulse of 200 seconds. The selected variant contains 3.7 kg of green monopropellant, and it is able to place a 12.1 kg Cubesat into a low-altitude beam flyby. The transfer time for this approach is slightly over 3 days and a half. Remarkable is the fact that gravity losses during thrusting account for a 20% increase in delta V as compared to an impulsive maneuver. This solution provides a single flyby and requires installation of a separate reaction console subsystem in the spacecraft. Moreover, it is only capable of lifting 4.9 kg of non-thrust-related mass. It was of interest to develop a low-energy transfer based on chemical propulsion. In doing so, an invariant manifolds approach as the one inferred by Mingotti et al. Was studied. The maximum initial mass of the satellite is 25.5 kg, and the only possibility is to have a perigee kick stage of 8U plus an onboard 4U module for lunar insertion. Nevertheless, Cubesat staging is not yet properly assessed, and the spacecraft mass besides the thrusters is extremely low at 3.5 kg. In order to study electric propulsion alternative, an enhancement of the model was proposed. Such improvement comprises the inclusion of drag and solar radiation pressure perturbations in the model, as well as an eclipse detection algorithm. Solar panels are expected to account for a significant amount of spacecraft cross-sectional area, and thus during low Earth passes, the air placed parallel to the flow, and thrusting is not performed. Similarly, during eclipses, thrust is turned off, otherwise the required batteries will be too heavy. The SRP perturbations were not critical from the maneuverability point of view, which was a welcome finding. The electric alternative makes use of a boosted P3 radio frequency ion thruster capable of delivering 1 mN of thrust at a specific impulse in the vicinity of 1900 seconds. Indeed, this is the selected operating range since the thruster can overperform such figures, providing a thrust of 1.24 mN at a specific impulse not lower than 2300 seconds. The resulting transfer is significantly extended in time, yet it allows to perform at least 3 low-altitude flybys, rendering it the preferred solution. Approach maneuvers are required for each of the 3 flybys, and the spacecraft ultimately escapes the Earth-Moon system towards an inner solar orbit.
Regarding the attitude and orbit control systems, I'm going to start talking about the electric thruster. One of the main characteristics is the maximum power of 80 watts, which will impose severe constraints to the solar power, as we will see later. But one of the main characteristics is its integrated reaction control system, having 2-axis gimbals which provide direct control in 2 axes and allowing to control the thrust axis through mirror image maneuvers, which has exceptional efficiency, and in order to account for this, a consumption of 0.24 millimeters of thrust has been reserved during the whole mission. Regarding the OCS sizing, a trade-off table including several attitude control systems, its performances and its importance regarding the emission requirements has been assessed, finding that the 3-axis stabilization was the best option mainly due to the pointing and maneuverability requirements. Regarding the environmental disturbances, the aerodynamic torque was found to be the most critical one, mainly during the low passes. Finally, in order to size the actuators, the momentum storage, the slew torque, and the actuator torque must be taken into account. Here you can see the reaction wheels, the final design in which the magnetic bearing concept has been used, which allows for zero wear, low friction losses, and so on, allowing for a higher rotational speeds, which induces higher momentum storage and life, but being more complex. Regarding the design, they have been designed for index optimization, moving the mass towards the outer rim, and a tetrahedral configuration has been proposed to allow for backup and a better maneuverability. All of this has been placed inside of one EU box with a total mass of 210 grams with a 50% extra. Regarding the OCS sensors, a sun sensor has been used, which is simple, reliable, and allows for backup, a star tracker for greater accuracy, and an inertial measurement unit for a fast attitude determination being integrated with the star tracker to unbias. Finally, regarding the pointing accuracy, a total system error methodology has been followed to account for all the possible sources of error. Here you can see the sun sensor accuracy, the star tracker one, which is much better than the sun sensor. But we have also taken into account the orbit determination, which is the most severe one, in which the Doppler shift would be the cheapest method for Cubesat. And in order to provide a typical value, the precision for a similar mission such as the lunar reconnaissance orbit has been used, which together with the lowest 5 passage can provide an estimation of the pointing error of the orbit determination. Finally, the other sources of error such as the wheel precision, computation error, or thrust alignment has been used for a conservative approach, ending up with a total pointing error using the star tracker or the sun sensor being lower than the 0.5 degrees in the requirements for the mission.
Regarding the comms and electric subsystem, I will discuss the comms architecture and antenna design, and then the power generation and electrical components used in the space. The communication subsystem is critical. There is no point in going to the moon if you cannot transmit back the data. Therefore, we must build into our system redundancy, reliability, and most of all some performance. There are 2 types of messages that we must transmit back to the Earth. From one side, scientific data, which is transmitted at a high volume, we are assuming 10 megabytes per flyby, and must only be transmitted once, right after a flyby. Telemetry and telecommand data, however, are transmitted continuously, every 10 seconds. However, it's a much lower volume message at only 1 kilobit. The communications take place between the spacecraft and some ground station. When choosing this ground station network, a balance must be struck between their cost and performance. ESA provides very high quality antennas in their S-track network. However, it is unlikely that it is cost efficient for this type of mission to use it. Therefore, we are assuming for our ground station network the same distribution of antennas as S-track, but with antennas of a much lower quality with a gain-to-noise ratio of 25. For redundancy purposes, we employ 2 antennas on the spacecraft. For the low transmission speed communication, an omnidirectional antenna will be mounted. These antennas provide low gain, however, they are very simple and do not require pointing. In this way, continuous transmission can be guaranteed at any point in the mission, regardless of orientation of the spacecraft and the thrust, requiring only 0.8 watts to operate. For the scientific data transmission, a patch antenna is employed. These antennas, while being directional, have a wide beam-width angle and provide medium gain. The choice of antenna provides a 8.3 decibel peak gain using 8 watts. With it, we are able to transmit 10 megabytes of scientific data in 5 hours. Moreover, patch antennas have a simple design that can be mounted on the side of the spacecraft. This antenna can be used to transmit telemetry data in the event of a failure of the other antenna.
Since we use electric propulsion, there are large requirements posed on the electric subsystem. The systems require 86 watts when illuminated that are reduced to 15 watts in eclipse conditions. This leaves us no choice but to implement solar arrays plus battery packs. The solar arrays generate the required energy to operate the spacecraft. They must provide 86.4 watts at end of life. This is made more difficult by the amount of time spent within the Van Allen belts, which will damage the arrays considerably. The damage is estimated at 20%. These requirements are met by the EHawk 112, which are high-performance panels that are very light as well. The batteries sustain the spacecraft while in eclipse conditions. It is a critical system without which operation is not possible. In the critical eclipse, the spacecraft consumes 24 watt-hours. Therefore, considering the number of discharge cycles, the GOME Space BP4 was chosen. It is relatively light and its 38.5 watt-hours of Li-ion battery will provide a considerable margin of safety.
For the design of the thermal control subsystem, ESET and thermal analysis software was used. We have defined two radiative cases, one maximum eclipse time case, computed by our MATLAB code, and one maximum solar irradiance case with no eclipse at all. The results show that every component is within its operative range for the whole mission duration. We also observed that the steady-state conditions were reached in the no eclipse case. This means that we are in the most critical scenario possibly encountered during the mission. To achieve this thermal stability, the thermal control architecture comprises passive elements like the surface finish, with two white painted faces acting as passive radiators, multilayer insulators to prevent the heat transfer from the thruster to the rest of the spacecraft, and also some active control elements, notably a switchable heat pipe to refrigerate the camera. This heat pipe contains a valve inside that can be closed to prevent excessive cooling during eclipse.
Regarding the structural subsystem, the following topics will be covered. We will start by going over the mass and volume budget. This table gathers the inputs from the different subsystems, adding up to a total of 8.7 kilograms with margins. The components which constrain the structural design can be found within the power subsystem. The B3 thruster requires a base of 2U, while the solar panels require a height of at least 3U. Thus, a 6U structure seems suitable, like the commercial off-the-shelf option by Endurosat, which has a structural mass of 908 grams, made of aluminum alloy. Is this a suitable choice? To determine it, we perform a preliminary analysis. First, the launch environment is characterized, in terms of natural frequency requirements, and elaborating a combined load factor Ni for each axis, following the advice of the NASA Ground Environmental Verification Standards. Next, the structure is idealized as a thin-walled cylinder, clamped at its interface with the launcher and sized against different scenarios. An iterative procedure is started to find the equivalent aluminum thickness and determine the required structural mass. The results show that backline is the sizing case, requiring a structural mass of 146 grams, placing the natural frequency safely above the minimum. By comparing with the conventional off-the-shelf mass, we may carefully conclude that the selected structural subsystem complies with the launch environment. In terms of configuration, the thruster shall be placed at the base, for obvious reasons. Above, the batteries are placed, to take advantage of the dissipative power generated by the B3, together with the reaction wheel complex, the blue box. On the top tray, the camera is placed, occupying a 1U cubicle. The other cubicle is reserved to the sensors and the onboard computer. The sun sensor is placed at 180 degrees with respect to the camera, to allow usage during the flyby. The star tracker is placed at 90 degrees with respect to the sun sensor, with the objective of optimizing its simultaneous usage. Finally, some brief comments on the mass properties. The center of gravity of the spacecraft at launch complies with the maximum static unbalance declared by the Soyuz manual. The inertia found in the different configurations does not represent sizing cases for the AOCS system. Finally, the choice of low thrust propulsion is not expected to raise resonant frequency issues with the solar arrays. To conclude, some main risks will be commented. The choice of propulsion exposes the spacecraft to long-term radiation through the Van Allen belts. Furthermore, there is lack of redundancy in some systems, the propulsion subsystem itself, which also presents a slightly low TRL level. The large panels might present structural issues, or even major issues for the mission if deployment mechanisms fail. Thank you for your time. It has been a great and fun learning experience participating in the contest.